Hi, my name is Manoj.
Hi, and I'm Alex, and we're going to present the comparison of solar, wind, and geothermal conversion for a HVAC system in a commercial building in Denver, Colorado. So today we're going to go over our introduction, which include our motivation and objective for this project. Next, we'll go over the background, covering the three energy conversion systems, solar, wind, and geothermal. And we'll also cover the social, environmental, and legal issues that are associated with each of these systems. Then we'll cover the methodology for the energy analysis, and then we'll cover the energy analysis for the original system, solar, wind, and geothermal systems. Then we'll look at the simulation models that we have for each of the systems. And then finally, we'll talk about the cost analysis and the future tasks. So currently in Denver, 50% of the green gas emissions are emitted from commercial buildings. And the Denver Climate Action Task Force has adopted a goal of reducing the greenhouse gas emission community-wide by 40% by 2025. So to help achieve this goal, HVAC systems in commercial buildings can be redesigned to help reduce the emissions being produced. So our objectives for this project are to determine how much energy consumption an HVAC system in a commercial building in comparison to solar, wind, or geothermal systems. Next, we'll analyze the capital investment, return of investment, and the maintenance cost of each of these systems. Then we'll run simulations to evaluate the efficiencies of these systems. And then lastly, we'll assess the reduction in greenhouse gas emissions in comparison to the original system.
So to go to a little background of the systems we're analyzing. So the first system we're gonna compare is solar energy. So solar energy is a renewable form of energy, so which means it uses the radiance from sun using photovoltaic cells. Solar energy is also cheaper and then a lot cleaner in compared to natural gas. And then, so since we're doing our analysis in Colorado, so Colorado was ranked 11th in the country for producing solar energy.
So there are three main types of solar panels, and they are monocrystalline, polycrystalline, and thin film. Each of these panels have advantages and disadvantages. So monocrystalline panels are constructed from a highly quality silicone, and due to their construction, they have the highest performance rating out of the three. And it's normal that they run up to a 21% efficiency. However, the downside of these panels is that they're extremely costly to manufacture, and that the manufacturing process produces a lot of waste. The polycrystalline panels are also made from silicone, but instead of being cut like the monocrystalline, they're actually poured into a mold. And due to this manufacturing process, it actually produces a lot less waste, making the panels more cost effective. However, their efficiencies are a lot lower than the monocrystallines, and they are about 13 to 16%. Lastly, we have the thin films, and these panels are lightweight and don't normally have problems when it comes to shade and obstruction, and they're very easily mass produced, making the panels themselves cheap. However, due to their build, you need to have purchased a lot more panels and support elements to help them match up to the first two. And they also don't last very long and have very low efficiency, which is normally between 7 and 13%.
So the next system we're gonna compare is wind energy. So like solar energy, wind energy is also a free form of energy. Wind turbines are used to convert wind energy into electricity, and which can be used for powering homes and for powering HVAC systems. Wind energy can also significantly reduce the carbon dioxide emissions. And in 2016, Colorado was ranked 7th largest in producing wind energy.
So there's two main types of wind turbines. The first one is the horizontal axis wind turbine, which is the most common one that you see. And then we also have the vertical axis wind turbine. So the benefits of the horizontal axis turbine is that they're constructed higher in the air, which gives them access to stronger winds. And this allows them to produce 20 to 40% more electricity than the vertical axis turbines. However, this does mean that maintenance is a lot higher to perform, as they are higher in the air. They also have to be shut off when the wind speeds get high, as the high winds can damage the components. So the vertical axis turbines is built a lot closer to the ground, which means the maintenance is a lot easier to perform. And they can also perform really well in high winds. And these turbines are normally found on high mountains or cliffs where the wind speeds can be dangerous. However, they aren't as efficient as the horizontal axis ones, as the wind speeds aren't as high closer to the ground.
So the last system we're gonna compare is the geothermal energy. Geothermal energy is the heat derived from below the Earth's surface, and it can be used to generate a clean and renewable form of energy. So the geothermal energy can be used in two ways. It can be used to produce electricity, and then it can also be used to heat space using geothermal heat pumps. So there are two different types of geothermal energy. So the first one is the horizontal ground loop. So these type of systems are mostly used in residential areas. It also requires a lot of space and it's cost effective, and the trenches need to be only 2 to 3 feet deep. So the next system is the vertical ground loop. It's mostly used in urban areas because it requires less space, but they can be very costly because it requires a lot of drilling.
So there are social environmental considerations that need to be accounted for each of these systems. So for the solar, there is hazardous materials, and these chemicals such as nitrogen trifluoride and sulfur hexafluoride have been traced back to the production. And also the disposal of these panels can be bad for the environment if they are damaged after decommissioned, as these chemicals can leak into the ground. Solar panel farms also require a lot of land to be able to produce enough energy, and this land can't really be used for anything else once the solar panels are in place. And then lastly, they also use quite a bit of water when they're cleaning the panels, just to make sure that the solar panels are operating at a high enough efficiency. So next, for the wind turbines, they cause wildlife endangerment and habitat destruction. So birds and bats can be killed by the turbine blades, and the turbines can also actually affect their migration routes of animals, which can cause them to die due to lack of food and energy once they take that deviated route. And then the disposal of the turbines is also an issue. So 90% of the turbines can be recycled, however, the blades cannot. And they have to be disposed of in a landfill, and they take up a lot of space. And lastly, the housing prices can be decreased as people don't like the look of the turbines. And there's also the sound and vibration issues that occur if the turbine doesn't have sufficient insulation, which can also deter people from wanting a turbine near their house. And then for geothermal energy, there is a potential for the ground to sink when the water and the steam is removed. And these geothermal plants are normally located near fault zones or hotspots, which are prone to instability, and the drilling could increase the risk of earthquakes. And then lastly, the air emissions have to be considered. Open loop systems can emit hydrogen sulfide and carbon dioxide. And then once the hydrogen sulfide is actually into the atmosphere, it can turn into sulfur dioxide, which can cause acid rain. So there is legal issues with each of these systems. So for solar energy, there is a financial incentive that are given to people who decide to switch to the cleaner energy systems to help overcome the capital costs. And there's also energy regulations in generating solar electricity, if it has to go through a third party or if the system is actually connected to the grid itself. And then for wind energy, there's regulations on how close the wind turbines can be to homes in the US, and it varies depending on the states. It can go between 300 and 1,000 meters. And there's also sound limits that turbines can produce, so they're not disturbing people. And there's also an issue of the downwind disturbance, and this is mainly an issue if there's quite a few turbines in the same area. So after the wind goes through the turbine, it actually decreases, and this would affect another person's wind turbine if they're downstream from that turbine. And then lastly, the permits are needed for disposal of the turbine blades, as they take up a lot of space in landfills. And then for geothermal energy, leasing and permits are needed as you'll be digging, drilling, and installing equipment into the ground. And there's also groundwater regulations, as you can't be putting harmful pollutants back into the groundwater after it's been used.
So onto our methodology. The first thing we did was calculate the energy used for our baseline system, so which is the natural gas electricity system. We did that using the Equest software to get all the energy used for the year for heating and cooling, and then the amount of cooling and heating required in ton. And using the baseline energy, we calculated the size of the solar panels that's required to produce the equivalent amount of energy. And then also using the baseline energy, we calculated the output of the turbine and the size of wind turbines we need to produce the energy equal to the baseline energy. And then for the geothermal system, we calculated the power input of the heat pump, and then the mass flow rate of water required for both heating and cooling to produce the required turn for our building. So we use the eQuest software to calculate the HVAC heat energy consumption for the building. So our assumption was it's a 2-story commercial building in Denver, Colorado, and we're using heat pump for both heating and cooling. So the following are the data obtained from the eQuest. So our equipment size was 11.25 ton, and the annual energy usage was 55,425 kilowatt hours. So using our baseline system, we calculated the area of solar panels and the number of solar panels that we need to use to produce the equivalent amount of energy. So our assumption was the solar panel yield is 15% and the performance ratio is 0.75. And the solar irradiation is constant, which is 5.69 kilowatt hours per meter square per day. And using the equation for the energy produced from the solar panels, we calculated the number of panels, which is 132, and the total area of the panels required was 237. For the wind energy, using the same baseline energy use, we calculated the output rating of the turbine and then the diameter of the turbine that we need to produce that amount of energy. So our assumption was the velocity is constant and the capacity factor is 0.4. The capacity factor is just ratio of the average output of the turbine and the maximum output of the turbine. And we assume that the velocity of air in Denver, Colorado is constant, which is 5.5. So using the equation for the output of the turbine and the capacity factor of 0.4, we calculated the output of the turbine should be 15.81 kilowatts, and then the diameter of the blade should be 22 meters. Onto geothermal system. For a geothermal system, we calculated the mass flow rate of heating and cooling, and then the input of the pump that is required to produce the baseline, the amount of energy equal to the baseline energy. So our assumption was the temperature of water is 55 degrees Fahrenheit, and then the air temperature during the summer is 80 degrees, and during the winter is 25 degrees. So using the first law of thermodynamics, we calculated the amount of cooling, the mass flow rate for the cooling to be 0.68 kilograms per second, and the mass flow rate of water for heating to be 0.56 kilograms per second. And then using the COP of the system, we calculated that the work input of the pump should be 10.42 kilowatts.
So we have simulations for each of our systems, and this is the Simulink model for the solar system, and it can be found by typing into the command window on MATLAB. So for this simulation, we modified the irradiance to match our value of 5.69 kilowatts per meter squared per day. And we also changed the size of the system, as originally it was 3,500 watts, and we needed ours to be 40 kilowatts. And we're also going to modify the number of modules in the string to be more similar to the desired model that we need. Next, we have the wind system, which we downloaded from the MATLAB website. And for this system, we modified the wind speed to match our value of 5.5 meters per second. And we also changed the pitch angle. So originally it was at 45 degrees. And after some research, we found that the optimal pitch angle was actually 35.5 degrees. And we're also changing the power of the turbine to match ours. And then next we have the simulation for the geothermal system. And this simulation was done in GOT-SOL software. And this software allows for the adjustment of groundwater, air temperature, and the size of the system. So we'll be able to obtain information if our system will actually meet the energy needs of the building or if we need to adjust the size. So for the cost analysis, we'll be looking at the payback period and the levelized cost of energy for each of the systems. So to do the cost analysis, some assumptions have to be made. So we're assuming that the project lifetime will be 20 years, And to be able to calculate the payback and levelized cost, we'll need to look at the cost in the present value. So we'll need to account for the discount rate, which is 3%, and the FEMP modified uniform present value, which is 13.89. And we will also be considering a 26% rebate, which is given in Colorado as an incentive to encourage people to invest in energy saving systems. So our future work includes completing the cost analysis to determine which system would be best investment money-wise. We will also be assessing the CO2 reduction, and then we'll finalize our simulations to represent real-life scenarios. So currently the simulations don't always account for the change in the weather temperature, such as the solar panels. They have an operating temperature of normally about 25 degrees. And we need to be able to account for that because in Colorado it does get very cold. And then we also need to account for the different changes in wind speed throughout the year. And these are our references. And thank you for your time.
Thank you.